Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session will be on the smooth particle hydrodynamics SPH. Right now on my screen what you are seeing is a animation is a drop of Coke or Pepsi or soda can. So typical tin can, inside that you have Coke or Pepsi, and that is dropping from a 5-meter height, and it is with some particular 10-degree edge angle it is dropping. So I just make a outer body transparent. Inside what you're seeing is the Coke, which we are represented as a water, which is a closer representation towards the Coke. So this is what example problem we are going to do step by step. So before going into example, just quickly we'll have what we are going to do. So guys, this will be our with a brief theory, this will be our third video on a smooth particle hydrodynamics modeling. We have done a droplet falling on a membrane, then we have bird strike, and this will be third one, a soda can drop test using in Abaqus explicit. So we are taking a typical can dimension. With this dimension we are going to model a can. This can are typically made of aluminium, so typical aluminium property what we are seeing is a 2770 kg per meter cube density, 73.1 GPM. Models will have some plasticity in this model. Water typically going to model using equation of state, and in equation of state we are going to use typically use some type where we have to give sound wave velocity within the water. That's what actually we are going to represent for the equation of state, and typical viscosity of water. Unit we are going to use is a ton millimeter Newton second. We have measured the physical thickness of these cans. We just cut and check. It is around very small thin section 0.004 inch. So since we are going to use SI unit, it will be 0.0102 millimeter will be thickness. Typical setup will be, we'll have a can which is not dropping on a face, it will be tilted at 10 degree. So if I measure from this floor, it will be 10 degree tilt. Inside we will have can, then we'll have water, and it will going to drop on the rigid plate. Now for whenever you want to do a drop test, even though you have to drop from the 5-meter height, we are not going to physically drop it from 5-meter height, because it will take a lot of time to hit the rigid surface, and we are not interested in between. There will be nothing happening, no stress generation, it is just free falling drop. So before hitting to this rigid plate, we calculate what will be the initial velocity for this. So physics we have this equation under root 2gh. So whatever dropping from height from say 5 meter, you under root 2gh. So 2 into you have gravity into height. If you do, you can calculate what is the initial velocity before hitting the rigid plate. And for this particular case, the initial velocity before hitting the plate will be a 9.9 meters per second. So we'll model this, we'll give initial velocity to can water, plate will be fixed at the bottom, and then it's going to drop it. So let's start it. So let's start modeling the problem. So first we'll quickly create a can. So we'll create can. It will be deformable 3D. Using shell revolution, we'll model it around. We'll give approximately 500. I'll first put a point 0, 0. So I get that point. Then I'll have a 27, 0. So I get a bottom point. Then I'll have a 33, 7. So I get another point. Then I'll have 33, 113. So I'll just fit it. So I got this top shape. Now next will be 27, 124. That is what the exact height of can, and then I'll have another point is 0, 124. So I just quickly create this using line. That's it. So we got this. We'll revolve it around 360 degree. And then we got a can shape. Now what we'll do, quickly create a property, create aluminium. We'll give a density 2.77 e power minus 09. It will be ton per millimeter cube. So we are using ton, Newton, millimeter second. We'll have elasticity, it will be in MPa. So 73.1 is GPa. I have to multiply by e power 3. 0.33 will be Poisson's ratio. We'll go to plasticity part. We'll give 170 as a yield, and then 340, around 340 we have 10% clean. So 0.1. We have done that. We'll create a shell section for this. Now this will be very small, 0.0102. so just let me check it first. 0.0102. so that's what actually we are using. Aluminum, we are done. Now I'll just assign this to the can. So we have done the assign, so it is changed the color. Now our first part is ready. Now let's create water. Water will be solid. Using revolution we are going to do deformable. So we'll have water body part 2. Zero comma 0, then we'll have 27 comma 0, then we have 33 comma 7, then we have 33 comma 113, then we have 27 comma 124, and then 0 comma 124. so I'll just fit it, and then I'll create a line. Now this particular you have to join this because we are going to create a solid. For can we are not put this line because it is just a skin. So we have done that. Yes, we have to reevaluate this around 360. So we are done with water. Now quickly create a property water, which will be a fluid. We are going to use density is around 0.94 e power minus 10. This will be ton per millimeter, so it is not like 1000 kg per meter cube, a bit lower, 940 kg per meter cube. We'll have EOS. For USUP we are going to use 1.45. Let me check it, just confirm it once. So it's a 1.45 e power 06, so 1450 kg per meter cube sound wave going through water. So this will be 0. We'll have a viscosity of 1 e power minus 09. So we are done with the viscosity. Now we'll create quickly a solid. This will be a water. Continue, and then we'll just assign this water. We're done. Now let me assign this to this part. Section water, done. So we are done with water. We have created the water property. Now quickly we'll create floor, which will be district rigid. Will model using a shell, so it will be a planar thing. So we are going to say floor, it will be a rigid shell 500. So let's create 0 comma 0 just for reference. Then you have 250 comma 250 minus 250 comma minus 250 fit, and then we'll create this. So we are done this. Now well, let's create now assembly. Now we created a 3-part. One is can, floor and water. We are not done anything. We are assigned the metal property section. We'll create all these 3 as a assembly or instance. So we are done that. Now we have to rotate the can. So can and the water. So we'll quickly rotate this. So this will be in position. So we are taking can and then water. You have to give the first point, and then axis will be, so I'm going to give rotate 90 degree about x axis, so it will be 1 comma 0 comma 0. So I've done that in 90. So I say okay. Now I'll just put in some view. So let's put toolbar on for viewport, and then for views also will put. So let's go to toolbar and then views. So now this is what exactly we are seeing. So we first we'll do one more tilt about y-axis. We'll rotate it about 10 degree. So we'll select can, and then you'll select water, and it will be about 0 comma 1 comma 0. So we are going to rotate about y-axis, and it will be 10 degree. So we have done that. You will see that is penetrating the floor. So we have to move this surface now. So we'll move can and water, both will select, and then we'll move by 0 comma 0 comma 6 millimeter up. So it will just up, it is not touching floor. So this is in perfect position. Now we'll do a couple of things before doing meshing. I'll go to property card, and I'll assign the reference point here. So reference point, because it's a rigid surface, so we'll give boundary condition everything on the reference point. So we put the reference point here. Since it will be a dynamic explicit method, it will be a drop test, so we need to assign some inertia property for this floor also. So we'll quickly create inertia property 1 kg something, it doesn't matter, but inertia property should be there, sufficient inertia property to create a mass matrix. So we've done that. Now we'll go to part, and then we'll select a water body. We'll do quickly some boolean operation like cutting and everything, so that will be good for meshing. So I selected this define cutting plane. I selected the edge, normal to edge. I selected the edge, and then I'll just cut it. I'll say cut it. So this way you can do better meshing. I'll also select can. Can is fine, I think there's no issue. Now let's go to meshing. Before going to meshing, we'll just quickly create the contact property. So contact interaction, so friction and all this. So tangential behavior, we are doing frictionless because there is a water and can involved. And normal behavior will say default pressure over closure as a hard contact. We'll create quickly a contact general, a self contact. We'll assign that property to that. We have done that. So now we are defined property and everything. Now we will do quickly a quick mesh. So go to mesh. Meshing you cannot do in assembly, you have to do meshing in part. So I select water. Now around, I'm going to put some fine mesh here, so I'm going to take 5, and then I'm going to use a particular meshing algorithm. For that I just done a cutting. So mid axis minimize mesh transaction, that's what actually I'm going to do. And then now this is, we have done that, we selected that. Now important thing is to assign the proper element type. It is a solid, but it will be PC3D, it will be a fluid particle. So I have to select this, then it will be explicit 3D stress. So you see C3D8R 8 noded, but then you have to make a conversion. This is important step. You have seen in all our SPH videos. So conversion to particle is the important thing. You say yes, and time is equal to 0. So at time is equal to 0, this mesh is going to convert into a SPH particle. We done that. We'll put a mesh. So we got quite a bit good structural mesh around now. Now we'll quickly mesh can. We are going to put 4 millimeters, and then we'll also put some good algorithm there. So chord dominated middle axis, that's what actually we are going to use. This will be shell element explicit. So it will be S4R. That's what actually we are going to use, and we'll say mesh. So we are done with that. Now only remained is a floor. Floor we are going to put around 10. It is a rigid thing, so let's assign this explicit rigid. We are already assigned, so let's mesh this. So we are done this. We created 3 parts. We created interaction properties, instant. Now we'll quickly give a boundary conditions. So go to load, boundary condition. So I'm going to give a end caster condition. So end caster will be on the floor. So I'm going to select that, done, and I'll say it will be end caster. So we have done that. Now quickly we create a set now for can and nodes. It will be can nodes. We have to give initial velocity on this node set. So nodes, we select all can nodes. We have done that. Now quickly go to water. We'll create that node set. So nodes, and then this will be a water node set. Done, and then we have created both the node set. Now we can quickly define initial velocity. You go to the load, you select predefined manager, predefined field, you select create, and then this will be initial velocity. So velocity you select, go to set, select can nodes, and then you put 9. It will be minus 9.9 e power 03. We'll create one more for water node. It will be minus 9.9 e power 03. So problem is ready for to launch. Now we can quickly create a step. We'll create it, can drop test. We'll select dynamic explicit 0.025. We created step now. Now we'll create a quickly a job. Create, we'll say can drop test. Write file, we'll write we'll just do a data check if there is anything issue. Let's get clarity on the data set. So it has gone to data set. Now it's let me check. It will just show. Okay, then it is successfully completed. So you see there is no issue with this. So we'll quickly submit a run now. So let me go to the folder. I'm running from the command prompt. Reason is then you can do a lot of give command like double precision and all these things. So 6145J is equal to, I'll just select the job name. 1 minute, where is the INP file? Let me check the INP file. We have INP file here. So we'll submit that interactive CPUs is equal to 4 I'm going to use, and I'm going to use a double precision. So we are running with double precision. So it will first go to pre, then explicit.x, then it's go to packaging, and then it is explicit. So its run is started. Just wait for till we get the results, and then we can discuss more on this. So guys, our job is done. So what you are seeing is trace generation. So now it hit can get rebound, and then it generated some trace. You see some buckling and self contact also happen immediately, a load transfer area through that edge. So let me put into a free edge, and let me clear this, put a transparency and then part instant. So you can see now it get bent here, so it hit, and then because of it rebound, and then it can have multiple hits, it can go back and hit, but we are just run for a 25 millisecond. We are not we just was interested to give you a tutorial with a smooth particle hydrodynamics. You can run this for more time, you can see the multiple hit also. Thanks a lot for watching this video. Again, the SPH emphasis on the CAN was to help Abaqus community mainly to go looked into rigid packaging, sloshing or flexible packaging area. Thanks a lot for watching the video. Don't forget to subscribe us or like us. If you have any question or anything, write to our channel or email us at theabacusacumen@gmail.com. Thank you. Bye bye.